A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. Why should two atoms share electrons? Let's take a look at these two fluorine atoms. They can come together and bond together and form fluorine, F2. Each of the two fluorine atoms has 7 valence electrons. When they bond together, they share the unpaired electrons, so that now they both have an octet. The Lewis structure then of F2 would look like this with the dots, or we can replace the shared electrons with a dash. We have lone pairs of electrons on the valence level that refer to electrons not involved in bonding. Each fluorine atom has 3 lone pairs. The molecule itself has a total of 6. We have one bonding pair that gives us that single covalent bond. Sometimes you're going to be asked how many lone pairs of electrons there are, or how many bonding pairs of electrons there are in a molecule. So here we have some more diatomic elements. You can put a bond here between the two fluorine atoms like we had a moment ago. The oxygen atoms, because they have 2 unpaired electrons, can share both of those pairs. And the nitrogen with 3 unpaired electrons can share all 3 pairs. And so we wind up with a single, a double, and a triple bond in these 3 diatomic molecules. How many lone pairs? Well, we can count them right here. 6, 4, and 2. Now in this slide we're taking a look at the single, double, and triple bond, and a couple things to note. First of all, that the single bond is the longest of the 3 and the weakest. Weakest meaning is the easiest to break. Whereas the triple bond would be the shortest and the strongest. You can see this verified in these table of bond lengths and bond energies. So if you compare the first 3 bonds, you notice how the energy increases and the length decreases. Also notice that the amount of energy doesn't double from a single to a double. Doubling would make it almost 700, and this is a little bit less than that. So we might have a double bond, but the 2 bonds aren't really equal. It's more like 1.5 or 1 3/4 of a bond. Because the single bond is the longest and the weakest, that means that the F2 molecule is the most reactive of the 3. In fact, the N2 molecule is so unreactive that most of our atmosphere is made up of this, and we breathe it in, we breathe it out, we can't do anything with it. But it also means that when N2 is formed in a chemical reaction, there's an awful lot of energy released from that triple bond forming. Now let's take a look at water. We saw this before. We have an oxygen atom with 2 unpaired electrons. We have a hydrogen atom we can bring in to make a bond here, another one make a bond here, and then we wind up with our structure for the water molecule. 2 lone pairs of electrons and 2 bonding pairs. Now we can take a look at ammonia. Take a look at the nitrogen atom first. Notice it has 3 unpaired electrons. So we're going to bring in 3 hydrogen atoms and bond them together like that. And then we can replace the bonding electrons with a dash. And here's our Lewis structure for ammonia. 3 bonding pairs, 1 lone pair. There are rules for drawing Lewis structures when you already have a formula. I'm going to go through that, and then we're going to draw out maybe 5 different molecules. First thing is to count all the valence electrons that are present in the molecule. Then we're going to draw the molecule. And if we have a molecule made up of at least 3 atoms, but only 2 elements, we're going to put the atom that's all by itself. Like for instance, if we had CO2, we'd put the carbon in the middle and then put the oxygens on either end of it. So we have to know how to set it up first. We're going to use a pair of electrons to bond the atoms together. And then we're going to complete the octets of all the atoms in the molecule, except for hydrogen because it doesn't have an octet. We will do the central atom last whenever we draw out molecules of at least 3 atoms. Now I'm going to go through drawing out some of these. If you want to try them on your own first, that's fine, but I will do them one at a time. Let's take a look now at the carbon tetrachloride. What we have is we have my arrow here. We have 4 valence electrons from the carbon, and we have 4 chlorines. Each chlorine has 7 valence electrons, for a total of 32 electrons. So I'm going to get my pen here. First thing I'm going to do is bond the atoms together by using a pair of electrons. And then I would complete the octets until I run out of electrons. don't have to be real neat with this as long as we get them all in there. So you notice now that each chlorine atom has an octet and the carbon has an octet. So now I'm just going to replace those bonding electrons with a dash. 1, 2, 3, and 4. And then I also put my lone electron pairs in. And there we have it. So this is the Lewis structure for carbon tetrachloride, 4 bonding pairs and 12 lone pairs. Next we have CO2. Okay, so we have 4 for the carbon and 2 times 6 for the oxygens. That's 16 electrons. So we start by bonding the carbon to the oxygens. We're going to go around the oxygens until I run out of electrons. And now that's 16 electrons. If the carbon doesn't have an octet, it only has 4. So I'm going to have to form multiple bonds for the carbon to get an octet. I'm going to bring a pair of electrons here and here up. So it looks like this. So these are my bonding electrons. Now the carbon atom can form multiple bonds. One reason why carbon is so reactive. Okay, I'm going to replace those bonding electrons with a dash. And there we go. So that's the Lewis structure for carbon dioxide. So what did you notice? The central atom didn't have an octet. We had to form multiple bonds so that the carbon atom could have an octet. So normally carbon atoms form 4 bonds, but it can be any combination of 4. 4 singles, 2 doubles, a triple and a single. Any combination will give us 4, even a double and 2 singles. All right, now we're going to do sulfur dioxide over here. There will be 18 valence electrons. And we start by bonding sulfur to the oxygens. We're going to go around. And that's all 18. So the oxygens are all set, but you notice the sulfur in the middle, 2, 4, 6, only 6. So I'm going to have to form a double bond with one of these oxygens. I think I'll pick the one on the left. I could pick the one on the right too, that won't matter. Okay, so this oxygen has 8, sulfur has 4, 6, 8. This oxygen has 2, 4, 6, 8. Good. Now I'm going to replace the bonding electrons with the dashes. Good. It's important not to put in too many electrons, so make sure you just use up the total that you determined in the beginning. So there's the Lewis structure for sulfur dioxide. We have a double and a single bond. We have 1, 2, 3, 4, 5, 6, 7 lone pairs of electrons. Next we have carbon monoxide. That has a total of 10 valence electrons. So we start here, bond them together. And quickly I use up my 10. But the carbon, again, only has 4 electrons. So I'm going to have to bring up 2 pairs and add them to the pair that's already there. So this is going to give me a triple bond. So you notice now I have my 10 electrons. These 6 count for both atoms. So the 6 and 2 for 8, 6 and 2 for 8. So that means I have a triple bond. Within carbon monoxide. Now the next one we have here is a polyatomic ion. You can see the negative charge on it. And this is only going to affect the total number of valence electrons. So we have 4 from the carbon, 3 oxygens are 3 times 6, and I'm adding 2 more because of the negative charge. If this had been a positive charge, I would have subtracted the number of the positive charge from the total. So I have 24 electrons. So we start off by bonding the atoms together. Go around and do the oxygens. And now I have all 24 electrons. Notice though the carbon only has 6. So I'm going to have to form a double bond with one of these oxygens. I think I'll pick the one on the left here. So there'll be 2 electrons like that. So there, now my octet for the carbon is all set. I'm just going to fill in then for the other oxygens. Okay, so this becomes then a double bond here, and then 2 single bonds. And I put in my electrons. Okay, so we're all done. Now, one thing they usually do with the polyatomic ions is they will enclose it in brackets, and then you see the charge on the outside. There we go. So that's our carbonate ion.